Let's look at a simple example of 2D site percolation. This is a graph of size 10. Each site has an independent probability of being occupied. We define a cluster as a path of closed sites. There are several clusters shown on this graph. The red sites are sites in a cluster connecting the upper or lower boundaries of the graph. If we increase the probability of a single site being occupied, eventually there will be a cluster that is large enough to connect the upper and lower boundaries of this graph. An interesting question is, at which probability such a cluster first appears. This time we look at a graph of size 50 times 50, we will gradually increase the probability from 0. We call the interesting probability critical probability or percolation threshold. For a larger graph, the graph percolates at around the same probability. We may wonder, is it possible to estimate the percolation threshold in a more precise way? The answer is yes, but we have two small problems to deal with. First, how do we know if a graph percolates exactly? For example, can you tell if this graph percolates or not? We can of course decide if a graph percolates by using breadth first search starting from a random closed site, but then we have to test through each site in different clusters and each search may cost a long time. There is also an easier but not as accurate way. We can estimate the probability by which there is a big leap of the size of the largest cluster in different sizes of graph. Our next question is, how do we know the size of the largest cluster in a graph? To solve this I implemented an algorithm described in the paper, a fast Monte Carlo algorithm. For site or bond percolation, by Newman and Ziff. The basic idea consists 3 parts. First, choose a random site on the graph and choose to close it or not according to the probability and the random number generated. Second, check if this site connected 2 separate clusters together. In this graph, yes. Last, add the size of 2 clusters. Each cluster has a parameter, size stored. After these steps, we can simply search each clusters all over the graph and get a maximum size. Note that the largest number of clusters we can have in a graph is L times L. Thus the cost of this search only takes L squared times of check. To evaluate the probability of big jump, namely the percolation threshold, we need to simulate a Python program to collect exact data. This Python program can change the size of a certain percolation network, and output pairs of data indicating the ratio of the size of the largest cluster to the size of the graph, versus the probability. After collecting data points for graph sizes of 50, 100, 300, 500, 600, we have Mathematica to plot for us. The result showed that the percolation threshold for 2D site percolation is near 0.59, as various journal articles suggested. This is a pretty accurate value.